I'll be on. I'll merge them. Some of them merge them.
Okay, cool. Should I continue or start?
Yeah.
I think it's. Okay, apologize for the technical difficulties. All right. I was talking about density and sparsity, and the idea is that we're going to define a set to be sparse if these limits goes to 0, and define a set to be dense if its complement is sparse, and being sparse is equivalent to this quantity, the number of strings containing the set with length n, to be literal O of 2 to the n. There is, if you're familiar with complexity theory, there is a different notion of sparsity. That instead of using literal O of 2 to the n, it uses replaces this with a polynomial. This is not the notion that I will be using here. Okay, now using this definition, using this concept, we can now define what we mean by these asymptotic notions of computability. Specifically for coarse computability, a set is coarsely computable if there is a Turing machine that this set here, that is, we require the machine to always halt, and the collection of things that the machine halts with the correct input, this thing must be dense. We can could always can also do it the other way around. We require the machine to require the machine to always give the correct answer if it halts, but we relax this by allowing the machine to not halt sometimes. We just demand that the set of things that the machine halt, this set itself to be dense. First, some examples. Every computable set is both coarsely computable and generically computable. So we are indeed generalizing the notion of computability to tolerate this, essentially to tolerate a bit of mistakes in this context. There are also sets that are not computable but become coarsely computable or generically computable. For example, if I take the halting problem, take the any enumeration of the halting problem, and add a string with n zeros to the set if n is in the halting problem and not that if it's not, then this set will this set itself will be fairly sparse. So we're taking the halting problem and stretching it into a very thin subset of the collection of all strings. So this thing will be both coarsely computable and generically computable, but it will not be it will not be computable. And perhaps for a more interesting example is that post-correspondence problem, which is a staple of a non-computable problem, but it is both coarsely and generically computable. So by combining all of these properties of whether we allow the machine to halt, to not halt, or we allow the machine to make mistakes, we have all of these notions, all of these asymptotic notions of computability. We have coarsely computable if the machine can make mistakes, but must always halt. So things here are total. Generically computable things here may not be total, but they the machine may never make mistakes. And if we allow both kinds of behaviors, that is, we allow the machine both to sometimes not halt and sometimes give the wrong answer, we have dense computability. And interestingly, if we disallow both, that is, we require the machine to always halt and to always give a correct answer if it gives an answer at all, we can still have make a notion of an asymptotic notion of computability that's still not all the way down to computable by introducing these a new symbol that just represents a I don't know, and allow the machine to return this symbol for a sparse amount of inputs. And it's possible to construct sets that are generically computable but not coarsely computable, and vice versa, and sets that are both coarsely computable and generically computable but not effectively densely computable. So this diamond is it does not collapse. None of these implications reverse. Any questions so far? All right. I want to talk to think not just in terms of what is computable or not, but think in terms of the degree structures of these things. And in order to talk about the degree structures, I have to decide what I have to define what the corresponding reducibilities are. So coarse approximation is a coarse approximation of E if their symmetric difference is sparse, and we define a set to be coarsely reducible to another set if for every coarse approximation of this set, this Turing machine when using this approximation as an oracle, this thing itself is a coarse approximation of the set A. So that so if you have this set A, and we can draw a bubble coalescing all of the sets which are coarse approximations to the set, and same thing for the set B. And essentially, for coarse reducibility, we need to the machine has to map this entire collection of things into this collection of things. So this is this has the interesting property, the behavior that this Turing machine will be working not exactly with B, but with some coarse approximation of B. It will make some. Its oracle will be slightly incorrect, but the output, the set that is computing, may also be slightly incorrect. So there is this balance here.
The Turing machine is required to always halt, or are you also?
Yes, for coarse reducibility, coarse things we require the Turing machine to always halt. Coarse things are must be total. I am. You could notice that here there is a single Turing machine for every possible coarse approximation. I could also this the uniform version. I could also talk about the non-uniform version by allowing a different Turing machine for every possible set in this the collection of things that are of the coarse approximations to be, but for the purposes of this talk, I will be shoving these concerns under the rug. Just second footnote is that we can essentially play this game also with the other notions of asymptotic notions of computability. For effectiveness, we get basically the same thing. For generic and for dense, because the objects are not total, we have to replace, instead of having a Turing machine, essentially Turing functional here, we replace that with an enumeration operator. But the moral of the story is the same. It's the same idea. Since now we have this notion of reducibility, we can we have an associated notion of associate notion of degrees by just essentially doing the same as we did for Turing degrees, that saying that two sets are coarsely equivalent if they are if one reduces the other and so forth. So this introduces a degree structure, and we can start asking the same sort of questions that we had for Turing degrees for coarse degrees and for generic degrees and so on. So just a recap for Turing reducibility or classical Turing reducibility. We say that these two sets, they form a minimal pair if neither of them are computable, but everything that is computable to both of them, under both of them, is computable in the first place. So that the idea is that if you have, say, these two sets, there will be things that are in the lower cone. There will be things that are under these two sets, and they form a minimal pair if the intersection is just the computable things. So they are, in a sense, they don't share any. They don't have any common. Any common computing power. They don't. Sorry, I forgot the term. They don't share any common expressive power in terms of Turing reducibility. And this is a fairly old theorem that there exist minimal pairs for Turing degrees. We can ask the same sort of things for coarse reducibility and dense reducibility and so forth. And it is known that for coarse reducibility and dense reducibility, there are minimal pairs. And in fact, there are measure one minimal pairs. So this is analog to Turing degrees, that we have that pretty much everything that you pick will be a minimal pair. And for generic reducibility, there is this theorem by Dennis Hirschfield that constructing a minimal pair for generic reducibility, and it's interesting that the proof of this theorem is very different than the proof of these first two theorems. That for these first two theorems, they feel a bit more measure theoretic in the sense that they the proofs themselves end up showing that conclude that there are measure one minimal things. But this proof is very different because it actually works with representations and preserving computations and so on and so forth. So it's a much more delicate proof. And a result of mine is that this added complexity is not it's not a bug, it's a feature. You actually need to do this sort of more delicate proof because there are only measure zero many minimal pairs for generic reducibility. And for effective dense reducibility, it is still an open problem. It is still not known. We can also play this game of minimal pairs, but we can try asking whether if we can do this with just a single degree. In the context of for minimal pairs, there may be more degrees behind both sets, but the thing is that their intersection must contain only the computable sets. For minimal degrees, we want that these between the set A and the set of computable things, there is nothing in between, so that we want the set A to be not computable, and everything that is below A will either be equivalent to A or will be computable in the first place. And also another an old theorem that there exists minimal Turing degrees. And we can, using essentially the same definition, we can ask the same questions for these asymptotic notions of reducibility. And it is the case that there are minimum degrees for coarse and dense reducibility, and it's still not known for the other two notions of reducibility. And I will be talking a bit about this proof next. Any questions? A small interesting, small side note that's it's a bit interesting that the for example, for the coarse reducibility and dense reducibility, recall this one, the machine must always halt, but the machine may make mistakes. This one, it may both make mistakes and not halt. And their properties, they are fairly similar. And so in that regard. And it turns out that for the for minimum degrees, it's also essentially virtually the same proof works for in both cases. Need a small adaptation, but the point is that the coarse and dense, they behave fairly similar in the sense that the additional ability to not halt sometimes, these don't seem to pose that much of a problem generally, which I think is an interesting thing. So the ability to make mistakes it's a much bigger leap than just the ability to not halt sometimes. For the remainder of the talk, I will be giving an explanation. I'll be showing you how to prove that there are minimum degrees for coarse reducibility. This proof is based on the proof that for Turing degrees that there exists a minimum degree below any given CE degree. So we'll be turbocharging that proof in order to make it handle the mistakes in the oracles of these coarse approximations that we have. I'll be talking a bit more about it later, but it's interesting that this construction of minimal degree below in any given C degree, I think, is the most complicated construction for Turing for minimal Turing degrees, and we actually need some of those features. We actually need the fact that it is below any given C degree. I'll be talking a bit more about this later. All right. This is the general setting. We want to construct a set A that has minimal coarse degree, and what we have to do is to show that every possible candidate set here that is below A, this set must either be equivalent to A, coarsely equivalent to A, or must be coarsely computable in the first place. We can simplify this a bit by taking into consideration only the sets that have this form, that are phi sub E of A for some E. In the context of reducibilities, this is like that we are considering just the reduction from this bubble to this bubble, this collection of coarse approximations to this collection of coarse approximations, but since the reduction must must work for every possible course approximation. In particular, it must work for the set A itself. So technically, by imposing this requirement, we're doing a bit more because we are handling some things that may not exactly be course reductions, but this does not matter. This is sufficient to show what we want to show. The general strategy is the following: we will build a sequence of trees, a nested sequence of trees. We'll pick a path in that is contained in the intersection of all of those trees, and we will use the tree T sub E to ensure that the requirement R sub E is satisfied. Just a small recollection. For Turing degrees, the basic tool, the basic tool is this concept of e-splitting. Say, suppose we have a tree. When we are we will pick a path in this tree. When we are when we are trying to reason about the sets of the form phi sub B of A, we will only have access to the image through a certain Turing functional phi sub B of this path. We say that the string is splitting if there is an extension that we can see in the image of this under this functional. We can computably find a proof that these two strings came from different paths. So if this is true, I mean, we say that if every string in T is splitting, this gives us this interesting property that if it doesn't matter where we are in the tree, suppose we are here, because the tree is splitting, we know that these two paths here, they will these two strings, they will the difference between these two things, they will show up in the image under phi sub B of A of both of these paths. So by figuring out, by trying out all of the possible, essentially searching for these things, we can figure out which of the ways we went when we're picking a path for inside this tree. On the other hand, if the opposite happens, that no string in this tree is splitting, it means that it doesn't matter which side we choose, the value of the image will be the same. So we have these two properties, that if every string is splitting, then the image will compute the set A, and otherwise this thing will be computable in the first place. So we are exactly in the setting that we want to be. Bringing into in the context of coarser usabilities, we don't have exactly the luxury of having a single from a single discrepancy in this thing to reconstruct the entire path. So I will relax the things this condition a bit. Fix certain K. I will say that this string is EK splitting if the same setting as before, that we find these two extensions. But now we require that to essentially have sufficiently many discrepancies on the image, so that if this will be the other path, or something like that, these two sets they will differ by a significant margin, so that when we are thinking in terms of just having a coarse approximation to these things, because for coarse approximations, the difference between the coarse approximation and the set itself must go to 0 as n goes to infinity. At some point, this will go below 2 to the minus k, and so this will allow us to do the same thing as before and actually figure out the path that we took when we were selecting this set. But this has a cost, that on the other case, when we don't have splittings, before the condition of splitting was just a single point of divergence. Now we have up to 2 to the minus k fraction of the divergence. So now, instead of knowing that this on the other case, instead of knowing that if T has no splits, then this instead of knowing that this will be coarsely computable, this will be just coarsely computable up to precision 2 to the minus k. That is the distance between the actual set and the set we can compute. It will the fraction will always be below 2 to the minus k, but it may not be 0. So we have this problem. And Joe Miller to the rescue. It's actually if we have a sequence of indices for sets that approximate the set B, exactly in that context of having progressively better approximations, we can actually show that the set B is coarsely computable. So this gives us a strategy. If we get if we make the k being progressively larger, we'll get progressively better approximations, and so this will give us the by using this theorem, we will know that this set will have a coarse approximation. And actually, we can even relax this a bit. That we may assume that we may allow the sequence itself to be 0' computable. The sets here those indices must still be delta 1 indices. They must be indices for computable things. But the sequence itself can be 0'. So this will be helpful. And it's interesting to note that we cannot replace this 0' with anything that is not delta 2. So that this is this generalization is as far as this theorem goes. So this is the strategy. We start with the complete binary tree, just throw everything, and then from here we define the next tree by aiming to be EK splitting. That is, suppose that once we define this, we know this string. We look at this. The corresponding point on the previous string, on the previous tree, and see if there is a pair of extensions that will be EK splitting. If it is EK splitting, we pick those. Otherwise, pick anything, and do the same thing for the next tree and the next tree, and so on. So as we progress through this collection of trees, as we progress through this collection of trees, we will have the following. For a fixed A, either we will succeed and have the one of those trees here be EK splitting, in which we can apply the previous argument, the idea that we can reconstruct the path from the coarse approximation of the image. Or we, for every K, we will fail. And say if this is for equals 1. So, and if we fail for every K, but for the same A, we fail for every K, then this one will compute, with this one, we can compute an approximation to the image with precision 2 to the minus 1, and this one 2 to the minus 2. And then as we go further, we'll get progressive better approximations, and then we can apply the Joe-Miller's theorem. This does not quite work, because if we simply, from here, we simply ask whether there is a splitting, then this question is a sigma 1 question. So this is not, this requires the powers of the halting problem in order to figure out. So this tree here will be 0 prime, and then this tree will be 0 double prime, because it's same construction on top of this, and so on. So in the end, if you do the analysis, the approximation that we get will be a 0 to the omega a set that is computable in 0 to the omega, that indeed it's a coarse approximation to the set, but this 0 to the omega is far away from what we want, that we want this to be computable. This is at least something that says that for this set here, the complexity of the things below it is bounded, so it's not ridiculous. It will not be of unbounded complexity, but this is far from what we want. So first thing to do is to do the construction by stages. Essentially, when at this point, instead of asking whether there exists a pair of strings whose extension, exists a pair of extensions to the string that is EK splitting, we add we pick an S and add a limit to every possible to everything in this computation, so that we will search for strings of length at most S. We will demand that the computation of that the computations that assure us that this is actually a split, we demand all of these computations to finish in less than S steps, and so on. So now we have a bunch of trees. So this tree will we'll analyze things only inside this tree only inside this tree, and so on. And now as S increases, these will as S increases, we get progressively closer to the construction that we had before. Define T star to be just the limit of these trees. So the thing at the end will be T star the limit. And now because each tree is a limit, This is a bit better than before, that the things are all of these trees are zero prime computable. And if you do the analysis more precisely, now we can replace the 0 to the mega with 0 quadruple prime. I'm sure you can count to 4, right? Better than before, but still not what we want. The next trick is that we don't actually need this thing here. This limit tree is it will be 0 prime computable, but we don't actually need the entire tree, because for example, if we had this path here, if we take out this part of the tree, the one that is not directly implied by the it's not adjacent to this to the path that we choose in the tree. This kind of doesn't matter, because we can always start asking this question whether it's e-splitting or not, starting at any point. So we can actually discard a majority of this tree and still have it work for our purposes. So we do the following. Besides asking, whenever we are going to look in the previous tree whether there are a pair of strings that is EK splitting, if we manage to find one, we pick that one and don't change it afterwards. We only change if, say for example, at this point, we only change it the selection if some of the if the previous tree itself changes. So by holding on to that to this choice as long as possible, we get the following this following property, that the say consider this point here. We know that because for this this is the first collection of things, so everything here is just the total perfect binary tree. And for this one, we will either know that we will either have that across along this path we will have something that is e-splitting, so that this task of always picking another e-split, this will either always work or it will eventually stop working. And if it eventually stop working, we can say, suppose it stopped working at this point, then we can prune the tree and only consider the subtree under this point, and under this string, and then from here now we know how this tree will behave. So this essentially we know we can compute when this limit will approach for this sequence of trees. So this will make this this means that if we ignore the rest of this tree, this part here it actually is a computable tree. So so now we have the sequence of approximations of these for these trees that is actually computable. Things become a bit more complicated here in the sense that the say if you're in this point, we have to keep track of both whether this thing will always succeed and whether these will always succeed. So and for this one, we have to keep track of whether these will always succeed and so on. So we have to keep track of progressively more things, but still a finite amount of concerns. And so for these doing this by doing this strategy, if you do the analysis, then because we downgraded from 0 prime to computable, this gets rid of one of the primes. So now we are down to 0 triple prime approximations.
Intuition correct to think that once you pick the path, along the path, it looks like a finite injury argument. Because you only change if the previous tree has changed along that path.
Yes, it does look a bit like a finite injury argument.
It's along the path, right? Because if I don't keep track of the final path you're going to pick, then it's going to be all over the place. But for the path that you're going to pick, it looks like a finite injury.
Yes, it does have this exact same behavior of that you have to keep track of everything that happened until now. So yes, along this path, you can think of this as a finite injury argument. But yeah, okay. The next step. Previously, we were constructing these things and then picking the path at the end, just taking the path in the intersection at the end. And we don't actually have to do that. We can actually interleave this computation by essentially interleave computing the next collection of trees and picking prefixes of the path. We'll do essentially we'll do the following. So for the first tree, we pick as some string and we force every single tree after that to contain that that string. And when we go to the next when you go to the next stage, we now do it at this point. We also pick a finite string and also demand it to contain every single be contained in every single tree. And same thing here and so on. So if we pick progressively larger strings, these will eventually this sequence of strings will eventually converge to a set that will be contained in every tree by construction. But now, because these things are interleaved, we since A is now a limit, now we have that A itself is 0 prime, and so if you do the analysis now, the sequence of indices can now be computed in 0 double prime. Just from this, we cannot conclude that that A is computable, because we have that it could be that, for example, at this point we will pick a string here, but it could be that these before that the corresponding string here changed, so we still need the limit. But interleaving this construction does reduce the complexity to 0 double prime. And finally, this part I will omit. It's a fairly technical thing that essentially we just do stack permitting on top of this argument. That the idea is that we pick a non-computable C set, and these we pick a low non-computable C set and only allow the tree here to change if the changes will happen in some will only happen if if the prefix of the things that are still the same, this is longer than some quantity that is defined by the set C. This is just using the standard permission construct. It ends up being a bit technical because now you have to drag across all of this construction, the set C, but the general idea is still the same. And because the construction works for any C set, and now if we choose this C set to be low, now when you do have to work to compute the sequence of approximations, the sequence of approximations will be computable in A prime. Before A was 0 prime, so this thing went up all the way to 0 double prime. But because this we did this construction below this low C degree, we finally have the sequence of indices, the sequence itself being 0 prime computable. We can apply Joe Miller's theorem and conclude that these sets that the set will be coarsely computable. And finally, I'm hiding. There is one more detail that we actually have to show that this set A is not coarsely computable itself, but this can be done using this construction. So I'll be showing that also showing that under the rug. And yeah, that's what I had to say.
Are there any questions?
Do you know if you can do better than just the minimal pairs having measure 0? Forget for what notion. Yeah.
For example, showing that they're only countably many or something like that.
Or yeah, Hausdorff dimension or something.
I don't know. I think I'm pretty sure that this argument can be modified to show that there are at least countably many. But beyond that, I don't know.
Question? Online? That was thank Tiago again.